We often take for granted the invisible forces that hold our universe together. Gravity keeps our feet on the ground. Electromagnetism powers our homes. And then there's the fascinating world of chemical bonds, where atoms link to form molecules. Two key players are lattice energy and bond enthalpy. These concepts are fundamental to understanding the stability and reactivity of substances. Imagine salt, a testament to the power of lattice energy. It holds sodium and chloride ions in a rigid crystalline structure. Bond enthalpy is the energy to break a specific chemical bond. Lattice energy shows overall stability, while bond enthalpy focuses on bond strength. Lattice energy measures the strength of electrostatic attraction between ions in a crystal lattice. It's the energy released when gaseous ions form a solid ionic compound. Higher lattice energy means stronger attraction and more stability. Influenced by ion charge and size, larger charges and smaller ions lead to greater stability. Magnesium oxide has higher lattice energy than sodium chloride due to greater ion charge and smaller size. While lattice energy deals with the overall stability of ionic compounds, bond enthalpy, also called bond dissociation energy, focuses on individual bonds within molecules. It's defined as the energy required to break 1 mole of a specific type of bond in a gaseous substance. This is an endothermic process, meaning it requires energy input to break the bond. Think of it like this. Imagine trying to separate two magnets stuck together. The force you need to pull them apart is akin to bond enthalpy. The stronger the bond, the more energy you need to break it. Take water as an example. The bond enthalpy of the OH bond is quite high, around 464 kilojoules per mole. This means you need a significant amount of energy to break the bond between oxygen and hydrogen in a water molecule. This is why water is such a stable compound. Section 4. Periodic trends, predicting the strength of attraction. Lattice energy generally increases as we move up and to the right across the periodic table. This trend can be explained by the factors we discussed earlier: charge and size. As we move up a group, the ionic radius decreases, leading to stronger attractions and higher lattice energies. Similarly, as we move across a period, the charge on the ions generally increases, again leading to higher lattice energies. For instance, lithium fluoride, LiF, has a higher lattice energy than lithium bromide, LiBr. This is because fluoride ions are smaller than bromide ions, allowing for stronger attractions in the crystal lattice. Similarly, magnesium oxide, MgO, has a higher lattice energy than sodium oxide, Na2O, because magnesium has a higher charge than sodium. Section 5. Exceptions to the rule, when size matters. While periodic trends provide a useful framework, there are exceptions to these general rules. One notable exception arises from the significant size differences between cations and anions. In some cases, the cation can be so much smaller than the anion that it can't effectively pack into the crystal lattice. This leads to a decrease in lattice energy. A classic example is lithium iodide, LiI. Lithium ions are much smaller than iodide ions. This large size difference leads to less efficient packing in the crystal lattice, reducing the overall lattice energy compared to what would be expected based solely on charge and size considerations. Section 6. Conclusion. The interplay of energy in chemical bonds. Lattice energy and bond enthalpy are essential concepts for understanding the energetic landscape of chemical bonding. Lattice energy governs the stability of ionic compounds, while bond enthalpy quantifies the strength of individual bonds. These concepts, intertwined with periodic trends and exceptions, help us predict the behavior of substances, from the simple act of salt dissolving in water to the complex reactions that drive biological processes. As we delve deeper into the world of chemistry, we begin to appreciate the intricate dance of energy that dictates the formation and breaking of bonds. Lattice energy and bond enthalpy are not just abstract concepts, they are the very forces that shape the matter around us.